Hello, students. So I'm back with a new chapter, and you can see the chapter's name. It is called Dawn of Modern Physics. So, just start this chapter, just to introduce this chapter, I'll be telling you about two kinds of physics. There is one type of physics that is called the classical physics, and there is this other kind of physics which is known as the modern physics. So what's the difference between these two types of physics? Let me just write it down and then I'll explain it to you. Okay, so classical, and we have modern physics. So there are uh, a lot of differences basically. So we'll just see three main differences. The first one will be that the classical physics is based on the Newtonian mechanics. What is it based on? Newtonian mechanics. Newtonian mechanics. While if we look at the modern physics, it is more like it is more based upon quantum mechanics. Quantum mechanics. Okay, the next difference. In classical physics, we'll be dealing with objects which don't have massive speeds. Like they'll be moving in daily life speeds. Okay, so objects are moving with low speeds. And the example would be the daily life objects, even the bullet train. Okay, so in quantum mechanics, we'll be dealing with high velocity objects, high speed objects, high speed objects. Okay, so these objects would be moving in would be having speeds which are comparable to the speed of light. Speed of light. And what is the speed of light? Let's see. Okay, so the speed of light is 3. Wait a second. 3 into 10 raised to the power 8. This is the speed of light. Meter per second. Okay, sorry, just a second. Yeah, here we go. So the next difference is that physical quantities such as mass, length, and time are constant in the classical physics. So mass, length, and time are constant, while in modern physics these are not constant. Mass, length, and time in modern physics are not constant. Okay? So we'll just add not constant. Okay, so this was just the introduction of the chapter, and we'll be dealing with modern physics more. Okay, so we'll be dealing with modern physics a lot of times in this chapter, because in the modern physics we'll be studying about particles, we'll be studying about quantum theory, and we'll be studying about the Compton's effect, photoelectric effect. Maybe we'll be studying about the Einstein's theory of relativity in this chapter. So it's going to be a really fun, a really interesting chapter. So let's get started. Let's move on to the next topic. Oops. Yeah. So let's talk about Planck's quantum theory. So I'll be drawing a diagram just to make the concept clear. Just change color. Okay. So suppose the yellow dot that I put in the middle of this circle is the nucleus, and the blue thing, the blue circle around it, is the orbit. And I'm going to be drawing an electron, which will be red in color. Okay, so here is the electron, a teeny tiny electron. So when the electron gets excited, this means that it's absorbing some kind of energy, and this energy will be in form of quanta, and it's like packets of energy. You go to the general store or you go to the supermarket and you want some kind of packets of something. For example, you want some packets of Doritos or something, and you want 1.5 packets of Doritos. So the shopkeeper won't be giving you 1.5 packets. The store won't be giving you 1.5 packets. The store will be giving you either 1 packet, or it will be giving you either 2 packets. It won't be giving you 1.5 packet. That's how the photons work. This electron in red will be absorbing either 1 quanta, 2 quanta, 3 quanta. That's how it will be absorbing energy. Okay, so absorption and emission of light takes place in forms of energy packets or bundles of energy called quanta. Energy of each quantum is directly proportional to frequency, which is written in yellow. I'll just highlight this. Okay, this is mu, this thing in yellow that I'm shading right now. This is mu. This means frequency. And when we remove the sign of proportionality, E is directly proportional to mu. When we remove the sign of proportionality, we will put a constant, which is h, this constant. And h is the Planck's constant, hence the Planck's quantum theory. Okay, the value of h is 6.63 into 10 raised to the power negative 34 joules second. Okay, I'll just write it down for you. You can note it down in your notebooks if you want to. 6.63 into 10 raised to the power negative 34. And the unit is very important, joule second. That's the unit, okay? So if we derive this formula for like how it's related to the speed of light and how it's related to wavelength, we'll see that mu is equals to c upon lambda. Okay, so mu is equals to c over lambda. Okay, so we can just put this thing in the place of mu in this box here. So how would we write that? We'll write that as E is equals to H C over lambda. So what is lambda in here? This lambda that I'm circling over here is known as wavelength. What is it? Wavelength. So if you don't know what a wavelength is, let me just explain it to you. So the thing that I'm drawing in here is a wave. Okay? So this thing is the, wait a second, just draw a line. Okay, so this part is called the crest and this part is called the trough. One crest and one trough would make one wavelength. One crest and one trough would make. Okay, so as I was saying, one wavelength is one crest and one trough. I'll just draw it again. Okay, one crest and one trough. This is the crest and this is the trough, and they both unite and make one wavelength. Okay, so that's how we just derive the formula. E is equals to hc over lambda. E is equals to hc over lambda, which means the energy of a wave would depend upon its velocity, and the energy of a wave would depend upon its wavelength. It will be inversely proportional to the speed of the wave and would be, the wavelength of a wave, and would be directly proportional to the speed of a wave. Okay, now let's talk about photons and what they are and what their mass is. Yeah, I'm talking about mass. Even though photons are energy, they do have mass, but not when they're at rest. They have mass when they are in motion, and that mass is known as the effective mass of a photon. Okay, so let's see what a photon is. Okay, so let me just put a heading in here. Photon. Okay, so a photon is a particle that has no charge and its rest mass is zero. Okay, so pretty much it's a really easy definition. It has a zero mass at rest. But if we're saying that photon has no mass, this would mean that it has no momentum. But it has a momentum. Its mass is not zero. Like its resting mass is zero. Like when it's at rest, its mass would be zero. But when it's in motion, it will have an effective mass, okay? Effective mass. So how do we find that effective mass? So the effective mass, also known as M, will be given as M is equals to E upon C squared. C squared. Okay, this is from the equation of Einstein. E is equals to mc squared. That's where m is equals to E over c squared come from. E is equals to mc squared. So that's why m is equals to E over c squared. Okay, so if we want to write it in terms of mu, mu means frequency. So if we want to try and write it in terms of mu, we know that V is equals to F lambda, right? Okay, so V is equals to F lambda, where V is the velocity, which is for light it's c, and lambda is wavelength, which is mu in this equation. Okay, so mu will be equals to, if we equate it for this one, mu will be equals to V over F. Okay, this will be mu. Okay, wait a second. This would not be V, but it will be C. Okay, so this will be C because we're doing it for light, and velocity of light is represented by C. Okay, so mu will be equals to C over lambda. Okay, if we want to equate it for C, like in this equation, we would want to write it as C is equals to, oh wait, yeah, so we will want to write it as M is equals to E upon C lambda squared, whole squared. Okay, just a second, let me erase this thing. Okay, so M, which is the effective mass, will be equals to the energy divided by C and lambda. And you might want to square these terms. Okay, so C squared and lambda squared. That will be the equation in terms of wavelength and velocity. There's also another formula where we have M is equals to h mu upon C squared. So it's not important where this came from, but its application is important. So we're writing it in terms of this. This is frequency, mass in terms of frequency. Okay. Now we have another formula where we write M is equals to h over C lambda. So we have discussed a few formulas of the effective mass of a photon. So let's just, this is formula, wait, yeah, this is formula number 1, and this is number 2, this is number 3, and the last one will be number 4. So we've discussed 4 formulas. Okay, so the effective mass is also known as the kinetic mass. And now let's move on to the momentum. As I have discussed earlier, they do have a momentum since they do have an active mass. So let's see what their momentum will be. Okay, let me just erase everything. Yeah, yeah. So we're discussing effective momentum. Okay, so here we go. So the general formula for momentum will be P is equals to mv. But for light we will be writing VSC. This will be the general formula. But this equation will be driving other equations. Like we'll have P is equals to H mu over C. Okay? And we'll have another one which is P is equals to H over lambda. P is equals to H over lambda. Okay, we did not discuss the SI unit of the effective mass. So effective mass would be like, of course, it will be like, uh, it will be kilograms. The mass will be measured in kilograms, and the effective mass is also known as the kinetic mass because it's because of motion. And the momentum of the elect the proton, no, not the proton, sorry, the photon, is because of the effective mass, which is due to motion. Okay, these are the three formulas that we have discussed up till now. So let's move on to another topic, which is interaction of photon with matter. So we'll just erase everything and we'll have, okay, yeah. Mm, so, okay, so, yeah. So we have these topics or these subtopics for the interaction of mass with matter. So we've got three phenomenons: the photoelectric effect, the Compton's effect, and pair production. So first of all, we're going to be discussing the photoelectric effect. So the first scientist who observed this effect was Henry Schurz, and he observed this in 1887. And this phenomenon was successfully explained by Einstein. So what happens in this phenomenon is that UV rays would fall on a metallic surface, and this in turn would cause electron ejection from the metallic surface. And it needs a flow of current, of course. Okay, so you can see that in here, in the glass tube, the tube that's drawn with green color. So it's kind of like an open circuit. I've drawn the yellow for the UV rays, and you can see the UV rays falling onto an electrode, and the electrodes are not connected by any physical means. But when the electrons are ejected from an electrode, the negative electrode, they would flow towards the positive electrode. This in turn will produce current, and like that, you'll see that the current will be flowing, and this open circuit would no longer be an open circuit. Okay, so there are a few laws of photoelectric effect. The first one is that when we increase the intensity of light, the number of photoelectrons increase. So intensity increases, number of photons increase. No, not photons, but photoelectrons. I'm sorry. Photoelectrons increase rates. Okay. Now we can also write it as number of photoelectrons is directly proportional to the intensity of light. Or photoelectric current is directly proportional to the intensity. Let's move on to the second law. On increasing Why am I writing it all? Okay, so increasing the frequency of light, kinetic energy of photoelectrons would increase. So kinetic energy of photoelectrons, kinetic energy of photoelectrons would increase, okay, increases, okay, and this in turn would increase the frequency of light. No, I'm saying it a bit wrong. I'll correct myself. So when we increase the frequency of light, what's the frequency? Like waves per minute. That's the frequency, or waves per second. That's called frequency. Okay? Number of waves per unit time. So when that increases, this in turn would increase the kinetic energy of photoelectrons. Okay? Frequency increases. Okay? And the third law. There is a certain frequency called the threshold frequency, below which this effect does not occur. For example, the electrons need need us like maybe 10 joules of energy to eject. If you're giving it 9.9 joules, 9.99 joules, or like even a little less than 10 joules, they would not eject from the surface. They'll need the exact amount for the ejection of photons, photoelectrons. So there's threshold frequency required. Threshold frequency required for ejection. Okay. So what's the threshold frequency? As I've explained earlier, it is the minimum frequency required for the ejection of electrons. If the frequency is less, there will be no photoelectric effect. And there's a threshold wavelength. There's the maximum wavelength required for the ejection of photoelectrons, which is called the threshold wavelength. So if the wavelength is more than the threshold wavelength, the photoelectric effect will not occur. Okay, now how do we calculate the maximum kinetic energy of the photoelectrons? You know, let me give you an example. How would we even know that there's a kinetic energy of these electrons? Like, we know they are moving, but how do we determine their kinetic energies? When we give them the energy, like when we give them the energy to eject from the surface of metal, if there's an excess amount of energy, like the threshold energy is the minimum amount of energy required for them to eject. But if their energy is like a little more than that, the difference between that energy and threshold frequency, sorry, threshold energy, uh, yeah, that difference would be converted into the kinetic energy of photoelectrons. So we'll calculate it by like this, okay? I'm writing the formula in here. K E max, which means maximum kinetic energy. MAX. Okay, sorry. Is equals to E V naught. Okay, this V naught will be the stopping potential, and the E will be the charge of electron. Okay, now what's stopping potential? Yeah, so what is the stopping potential? In here, you can see that we are like the the UV rays are falling onto the negative plate, the negative electrode. But just in case, like just suppose that it falls on the positive electrode, there would still be an ejection of electrons. But that ejection of electrons would be less as compared, like not really less, but those electrons won't be too attracted to the opposite plate. And as the voltage increases, the electrons that are attracted to the opposite plate would decrease in number. And there will be a time when these electrons won't be able to reach the opposite plate, which means no current will be flowing from positive to negative. And that voltage will be called the stopping potential. The voltage at which current stops flowing when the polarity is reversed. Okay? So let's write it down. You might want to write it down. It is a really important point. The voltage note that the polarity is reversed here, which means the negative pole is now the positive pole and the positive pole is now the negative pole. Polarity reversed. So the voltage at which electrons stop moving to the opposite plate. This voltage will be called the stopping potential. Okay? Now let's move on to work function. Okay? I'll just erase everything. Yeah. Work function. Okay, if you have any questions or if you have any queries, please feel free to text me or comment down below. I'll be really happy to help you with this. Okay? You don't need to worry. I'll help you with everything, okay? So, we were discussing the work function. What is the work function? So, when we discussed that there is a minimum amount of energy required to eject an electron. The minimum energy required to eject an electron from the metal surface is called the work function. Okay? So, what is it? It's the minimum energy required to eject an electron from the metal surface. And how do we represent it? We represent it by this symbol. This is called phi. I've drawn it really badly. I think I should erase it and draw it again. Okay, let's do it. Okay, here we go. It's better. This is phi. Okay, we also use the symbol for electric flux, but right now we're talking about the work function H, and this is mu naught. H is Planck's constant, and mu naught would be the threshold frequency. So the energy required to eject an electron, minimum energy, okay? It should be the minimum energy required to eject an electron from the surface of a metal. This is called the work function. And the excess energy will be converted to the kinetic energy of the photoelectron. So let's move on to the Einstein's explanation of photoelectric effect. Einstein's explanation. Okay, so what did Einstein say? Einstein explained the photoelectric effect on the basis of quantum theory of light. Electron would either absorb one complete photon or it would absorb none. If the energy is less than the minimum energy required to eject an electron, if the energy is less than work function, then there will be no photoelectric effect. Let's write it down. If E is less than phi, if E is less than the work function, there will be no photoelectric effect. No photoelectric effect. We would not have any ejected electrons. If E is equals to phi, which means it's equals to the work function, there will be a photoelectric effect, but there will be no kinetic energy. Okay? Kinetic energy will be zero. Zero. But there's a third condition. If E is greater than the work function, then there will be a kinetic energy, which means kinetic energy would not be equal to zero. Would not equal to zero, which means some of the energy will become the electron's kinetic energy. So the total energy of a photoelectron should be represented by this equation that I'm going to be writing in this box. I write it with a different color, so it will be more focused. E is equals to phi plus kinetic energy, which means the work function and the kinetic energy will be the total energy of a photoelectron. Okay? With this, we can find three formulas. I'll write it down. Okay, so I've written an equation in here. H mu is equals to H mu naught plus EV naught. We've discussed earlier that EV naught is the maximum kinetic energy of a photoelectron, while H mu naught is phi, the work function, and H mu is energy. Okay, so the kinetic energy of electron can be written as H mu minus H mu naught. Okay, but we can see that H is common in here. So we'll take H common, and when V is equals to V naught, which means when the frequency is equals to the threshold frequency, the given frequency of the rays, the photons, is equals to the threshold frequency. Let's see what happens then. If mu is equals to mu naught, then this whole factor would become 0. This will become 0, which means the kinetic energy will become 0. Right? So the kinetic energy will be 0 when mu is equals to mu naught. Okay, let's move on to our next phenomenon, which is the Compton's effect. Okay, so in the not the photoelectric effect, in the Compton's effect, when an X-ray photon falls on an electron, it scatters a photon and it scatters an electron. So in simple language, the scattering of a photon by an electron is called Compton's effect. The frequency of the scattered photon will be less than the incident photon. Okay, so V2 will be less than V1. Sorry, mu1. Mu2 will be less than mu1. I'll write it down. So mu2 so 2 will be less than mu1, which means this pink X-ray that I've drawn in here, I'm highlighting this ray, this will have a higher frequency. And sorry, yeah, I drew this symbol wrong. And this one will have a lower frequency, so let me change the symbol. Okay, yeah, this way, yeah. So before scattering, the velocity, no, not the velocity, the frequency was greater, and after the scattering, the frequency decreased. Energy of scattered photon will be less than that of the incident photon, which means E2 would also be less than E1. 2 would be less than E1. But the wavelength of the scattered photon will be slightly greater than that of the incident photon, sorry. Okay, the wavelength of the scattered photon will be more than the wavelength of the initial photon. Okay, charge in wavelength is called Compton's shift in wavelength or Compton's shift. Change in wavelength, sorry. Change in wavelength is called Compton's shift. So how do we calculate the change in wavelength? Delta lambda will be equal to h over m naught c multiplied by 1 minus cos theta, where theta is the angle of the scattered photon. As you can see in the diagram, there's a theta and there's a phi. The scattered electron has the angle phi, while the scattered photon has the angle theta. So that's how we find the Compton's shift. So if theta is equals to 0, there will be no shift in the wave, because cos 0 is 1. 1 minus 1 will be 0. So there is no shift in the wavelength, which means the shift would be 0. Okay, we should write it down. We should probably write it down. Okay. Uh, yeah. So when theta is equals to 0, since cos 0 is 1, there will be no Compton shift. Delta lambda would also be equal to 0. Sorry. Okay, what if the theta is 90 degree? Then there would be a maximum shift in Compton shift. It will be a maximum shift in maximum shift in the wavelength because cos 90 is 0. So if theta is equals to 90, then the delta H will be equal to, sorry, delta lambda will be equal to this term, not this thing, okay? We'll just remove the 1 minus cos theta, okay? So delta lambda will be equal to this whole term right here, not the 1. The 1 is not counted. If theta is equals to 180 degree, then again, no, wait a second. If theta is equals to 180 degree, we'd have a maximum shift, maximum Compton shift. Since 180 degree, cos 180 degree is negative 1, we'll have a maximum shift in the wavelength. Since 1 minus minus 1 would be 2. So this whole factor, which I have highlighted with pink, this whole factor would become this whole factor right here. This will be multiplied by 2, right? So if we write it down, if theta is equals to 180 degree, there will be the maximum shift. There will be a maximum shift in wavelength, which means maximum Compton shift. Delta lambda will be maximum. Delta lambda equals to maximum. Right? And it will be equal to 2h over m naught c. That's all for the Compton's effect. Let's move on to pair production. So let's see the diagram in here. When a gamma photon hits the nucleus, then the nucleus decomposes into an electron and a positron. This phenomenon is known as pair production. Decomposition of gamma photon into electron and positron pair. That's pair production, okay? So the pair production cannot take place in vacuum because if there is a nucleus, which means it means that the space is not empty. And when the space is not empty, this means that there is no vacuum. Okay, what is a positron? Positron has the same mass as electron, but it just has the opposite charge. The same magnitude, but it's positive. It's like a positive electron. Okay? In this process, the energy is converted into matter. Hence, pair production is also called materialization. Okay, what does that mean? An electron has an energy of 0.511 joules, and a positron has, no, not joules, it's mega electron volt. Okay, 0.511 mega electron volt is the energy of electron, and the energy of positron is also 0.511 mega electron volt. So when you add those two, you get 1.02 mega electron volt. And that should be the minimum energy of photon required for pair production. Okay? This is the minimum energy required for pair production, 1.02 mega electron volt. What is the energy of photon? The energy of photon will be h mu and equals to 2 m naught c squared plus kinetic energy and the kinetic energy of a positron and a kinetic energy of an electron. So the energy of the photon should be equal to 2m0 c squared plus the this amount of energy, the energy of photon plus the energy of electron. If the energy is given more than this amount, 1.02 mega electron volt, then this energy will be converted to kinetic energy. Like, okay, now the last topic here. Then we'll move to another chapter. The last thing, it's the annihilation of matter. Annihilation of matter is basically the reverse of pair production. In this process, two, like the electron and the positron, will combine and they will form a gamma photon. That's basically annihilation of matter. Matter converts to energy, and is the reverse process of pair production. So you've listened to me this long, and I am really, really glad you've listened to me. Thank you so much for paying attention and listening to me. I'll be giving my Instagram account and I'll be giving my email address. So if you want to ask any question, if you have any queries, please feel free to contact me. And I also do personalized sessions, personalized uh, teaching sessions. So if you want to enroll in one of those, you can contact me. Thank you so much. Bye bye. Thanks for watching.